So I have here the M&M scenario that we discussed in the introductory lecture. M&M Mars used to publish the percentage of each color of M&M that came out of each batch. Now, they've since stopped doing this, so these numbers might no longer be accurate, but that gives us something to test. Are these numbers still valid? Right, so in the middle column, the expected proportions column, I have the previously published percentages. And in the right column, I've got the results from opening several packages of M&Ms and counting up the number of each color for comparison. Now, before we go any further, we need to confirm that the requirements to use our goodness of fit test are met here. So the M&Ms are mixed at the factory and then poured into individual bags, effectively randomizing our sample. Our sample values are frequency counts, which are what we needed. That's the right-hand column. Now, to confirm the last requirement, that every expected category has at least 5 values, we need to calculate them. Right, so if you add up the sample values, you see that our sample size is 50. So to get the expected values, we just need to multiply each proportion by that size. So 13%. I'm going to politely ignore that these are percentages. Obviously, you make them into decimals before you multiply. So it'll be 13% times 50, 20, 14, and so on, all the way down here, right? Then if you get your calculator out and do the calculations, you get 6.5, 10, 7, 8, 12, and again, 6.5. Okay, so now we can see that the requirement is met. We do have at least 5 of each color in the amount that we would have expected to get from a sample of this size. Okay, finally, before we start calculating the test statistics, remember what our two hypotheses are. The null hypothesis is that the frequency counts agree with the claimed distribution, and the alternative hypothesis is that they don't. All right, now remember the formula for the test statistic that I'm going to squeeze in here. It's a chi-squared statistic, and it's equal to the sum of the expected values minus the observed values squared divided by the expected values. And if you've watched the other lectures, you know how I like to organize these things, right? Get everything into a table. So we have the expected and observed values. These are the values from the previous slide. The observed ones come from the sample. The expected ones are the ones we calculated. And then I just worked through the little formula there. I did O minus E, right? So for this first one here, that would be 6 minus 6.5. Then I squared that value, then I divided it by the expected value. So that is the formula here for our test statistic. So to get the actual test statistic, the final result, we just have to total up the values in this last column, and if you do that, we get that our test statistic is 0.4031. Okay. So now we need to use this to get a p-value. Right now, when you're doing a goodness of fit test, the tests are always right-tailed. So what we need here is the probability that a chi-squared variable is greater than 0.4031, and our degrees of freedom here is going to be 5. Remember, the degrees of freedom is 1 less than the number of categories. And if you go back to the previous slide, there were 6 colors. So the degrees of freedom will be 6 minus 1, right? That's going to be 5. Okay, now this probability, you can get this whatever you think, whatever method you like to use. I like Excel. Excel tells me that this is a vanishingly small number. There's 6 zeros, 2, 8, 7. Now, no alpha value was specified, but if we default to the standard 0.05, or really even something quite a bit smaller than that, because our p-value, remember this is our p-value here, our p-value is really, really, really tiny, right? So alpha is going to be greater than our p-value. So my conclusion is going to be that there is sufficient evidence to reject the null hypothesis. The null hypothesis says that the given frequency values were correct, right? So I would say that there is sufficient evidence to support the claim that the current proportions don't match the historical values. All right, so that's the basics of a goodness of fit test. Now, what we're going to do in the next lecture is where we're going to kind of go back a little bit and think about the idea of independence. You remember when we first started talking about probabilities, we did these and probabilities. The probability of A and B was P of A times P of B, assuming that A and B were independent, right? How can we judge that? I mean, we've got results for two variables. Again, how can we tell if they are independent of each other? Right? That's what we're going to look at it in the next section. That actually, and you'll see once we start getting into it, that really is just going to be an application of this goodness of fit test.